All right, Tony Furst with Armstrong Fluid Technologies here to discuss pump curves and system analysis. Take it away, Tony Furst. Thank you.
Thank you, Mr. Mormino. I appreciate it. Good morning, everyone. Hope everyone's having a wonderful day on this middle of December Thursday as we get ready for the upcoming holiday season. And so, hopefully, today we'll get to educate everybody a little bit about pumps and pump curves and what all that information on a pump curve really means. And then once you have all that information, what do you do with it when you're standing in the mechanical room looking at the pump? How do you do something with it so that it makes sense? So at the end of this today, my goal is so that everybody understands the component parts of a pump curve, so that you understand what a system curve is, what you understand what a control curve is, and what the difference between a system curve and a control curve is. And then as well, how to use a pump curve to validate flow and performance. Now, when I look at my here wants to misbehave. As we look at pumps and pump systems, we got to understand some real simple basics. And the whole team between the engineer, purchasing, maintenance, contractor, the rep, everybody has to be involved in this scenario. Okay. Engineers are concerned how it works. Quite simply, that's what it really comes down to. Contractors, they're concerned, how do I get the system installed and running? Building operators, how do they keep it running? Along with that is the maintenance cost. What do I have to do to maintain it? And of course, purchasing, we all know how wonderful that is. They're all worried about first costs. And each one of these groups has a stake in the process. Each one of them also thinks theirs is the best rationale. And when you look at it and you understand what we're doing with pumping, you have to look at all these different stakeholders and look at the total system and figure out what really makes the best sense in upfront cost, life cycle cost, everything else to understand the whole system. Okay. Now, when we look at pump systems, one thing that we've found over the years is we have found that most pump systems are oversized. This is not a bad thing, and it's nothing against any of you that are consulting engineers. There's nothing wrong with it. But what happens is what we found is that one, we all put safety factor in. I was a design engineer before I came to work for Armstrong, and we all have safety factors that we apply to our designs because we can't control the construction exactly. So that leads to some oversizing. That's the first thing. The second thing is we have to understand that we got to look beyond energy savings. Okay. We got to look at the entire system. And one of the things when we look at energy cost, we can't look at it just at that first year energy cost. We've got to look at it over the lifetime of the building. We really have to make sure we understand life cycle costing and what that really means. And so this is why understanding pump curves and understanding how to interpret the data from a pump curve is really, really critical to being able to go out and figure out where your system is really running and determine how far oversized your pumps may be. Now, it's getting better as we've moved into the era of computerized design and doing piping system evaluations via computer instead of doing them the way I learned how to do it with a green sheet spreadsheet and pencil and a slide rule. Yes,
Hmm.
I am that old. Um, Things have changed a lot, so it's gotten better. But if you go in and you do a lot of retrofit work, understand that there's probably opportunity to downsize pumps in an existing building to get them to more closely match the system dynamics for flow and head.
And that's important for efficiency too, correct?
Oh, exactly.
So
And
if
we're
you
going to talk
oversize a
about that.
pump, you could be safer. Or you're going to talk about that. Okay, I won't steal your thunder. So what's the like in the industry today? How would you rate the average designer's ability to read pump curves? Is it something that has gone to the wayside, or something that's always been a challenge, or what are your thoughts on that?
Overall, Tony, what I'm seeing is that most engineers kind of sort of understand pump curves. They understand
Hmm.
some of the information that's being presented, But when we move into variable speed pump curves and optimized pump selections, a lot of engineers and contractors and tab contractors don't understand. They really got to pay attention to the data that's on the curve, because I've had a couple of jobs here recently where they've come back and said, "Oh no, you built the pumps wrong. They have the wrong impellers in them. You know,
Hmm.
tested." And I'm looking at what they tested, and they tested at different speeds than what the pump was designed for. And I'm going, guys, you tested it at the wrong speed. Reduce your speed to here, which is what the maximum speed for this pump was, and retest your shut off head. And they come back and go, "Oh, wow, you were right. We were wrong." And I go, "Okay." And I've had engineers call me and go, "Well, how do I know what the flow is? I've got a pump curve, but I don't know how to get
Hmm.
this information." So hopefully today we're going to kind of talk about that a little bit and get everybody to understand, what do you do when you're standing in the mechanical room.
Right.
Um, so hopefully this will enlighten people a little bit, um,
Great.
and make everybody's job a little bit easier. What I'm finding, from an engineering level, um, it's about 50-50, on engineers that really understand pump curves and engineers that don't really understand pump curves
Right.
at a deep dive level. So hopefully we can enlighten a whole lot of people today. So before we start talking about pump curves, let's kind of talk about what a pump is, okay, and what the parts of it are. Okay, in really simple terms, you've got an impeller or impellers, because we make multi-stage pumps, and those are just impellers that are in series with one another, which is no different than building pumps in series with each other. We have a volute, which is the big round part of the pump. We have the casing, the body, the housing. There's maybe a diffuser in it. There may be a bearing assembly, depending on whether it's vertical inline or horizontal in suction pump. And then we have a driver. Okay. Now, we're not going to talk about whether it's constant speed or variable speed, and whether you have a starter or a variable speed drive on it, because that doesn't affect the pump construction in and of itself. All pumps all have the same basic component parts. And so you got to understand those parts that are in there, and understand those parts are fixed by us as pump manufacturers. We decide what size the casing has to be, what size the impeller has to be, to optimize motor horsepower to flow and head that you as the engineer need for your system. Okay. So if we look at pumps, how do we determine flow? Well, that's what engineers are going to do. They're going to tell us what flow they need in the system. So if it's a booster system for a domestic water system, it's based on fixture count. So how many plumbing fixtures are out in the building? How many water supply fixtures are out there? You turn it into water supply fixture units, and you can use Hunter's curve or IATMO's water demand calculator or any number of other sizing tools out there, and tells you how many gallons per minute you have to have. For chillers and boilers, we're either looking at tonnage or we're looking at, design delta T, given the heating output of a boiler. So it's also based, it's on that BTU load calculation. And if we're looking at drainage coming off a roof, or designing a sump pump, it's all based on square footage. So that's how we determine flow. That tells us different flows that we need for different systems. So what do we do about head loss? Okay. Well, when I look at head loss is all the static requirements plus the head loss of moving water through the piping system. Okay. Now, the static requirement is only a critical component if we're talking about an open system. If we're talking about closed loop system, the water that goes up also comes down, and those two numbers offset each other. However, if you have an open system where you have an open cooling tower, then we have to worry about static head. And we have to worry about static head on both sides of the pump for suction head and discharge head. And those two are additive in that case. So understand, depends on whether it's an open system or closed system, as to whether we're dealing with static or not. Um, Velocity head really has a very, very small impact on total head in most HVAC applications. Now, I'm not telling you that it doesn't, but in most HVAC applications, it is minimal. Okay. So when we look at a test rig, and what you're seeing here, the pictures that I've got up on the screen are a HI test rig setup. Okay, so we build pumps to the Hydraulics Institute standards. We have to, just like every other pump manufacturer. And when we look at this, this is how we set up, and this is the way we test. Okay, understand that when I'm doing my test setups, I want to be 2 pipe diameters away from the pump on the suction and discharge side. So one of the problems that we run into is test and balance contractors or somebody out there trying to read what the pump is doing. They usually put the gauges in the gauge tappings that we've installed in the casting of the pump. Don't do that. If you look at the pump and you look at the velocity through that pump, the velocity is extremely high on the suction side and on the discharge side of the pump. It's part of the design of the pump. If you read the pressures at those points, you have to account for um, velocity and velocity pressure. Okay. So, in the velocity head that's imparted to it. So, what we recommend is, and from a design perspective, what I'd really like everybody to be able to do is design their system so that you can put Pete's plugs 2 pipe diameters downstream of the suction and discharge flanges of the pump. So we get really nice, neat, clean flow. We don't have a velocity head impact on our readings, and we get really good measurement data. Okay. So understand that if we have a big, huge change in elevation from where these readings are at, so if you're taking readings up near the ceiling and down near the floor, elevation may play into it if the pump's not running. Okay. So understand that pressure is nothing more than force per unit area, and it's in the U.S. here. It's measured in psi. Absolute pressure is the pressure exerted by the weight of air above it at any point in the Earth's surface. Okay, for most places, it's 14.7 psi at sea level. If you are designing a open system, keep this in mind. Gotta pay attention to elevation above sea level. I had a job earlier this year. The job is 2,000, just a little over 2,000 feet above sea level. The engineer did all his head loss calculations for the cooling tower and did it based on sea level. Well, guess what? At 2,000 feet above sea level, atmospheric pressure is not 14.7 psia. It's about 12.9. Don't hold me to that number. I'm doing it from memory. And at my age, there's a lot of stuff rattling around in my head.
Mm,
Um, So understand that you got to pay attention to sea level and where you're at in relationship to sea level. You know, Tony, you're in the mountains of North Carolina. What's your elevation above sea level there? Do you know?
about 2,500 feet.
Okay. So if you're designing up in the mountains where Tony's at, you know, you got to readjust your atmospheric pressure to be 2,500 feet above sea level. Okay.
Mm,
Got to pay attention to that because it will come back and bite you.
that's a hard one
Um,
to fix too.
Yes, it is. It is not pleasant to fix, and I really hate to be the guy to tell you that. As you know, when I talk to engineers, because a lot of my job I spend out working with engineers, helping to figure out why their system isn't doing what they thought it was going to do.
Yeah. Adding more pumping power is not easy
No,
in
no,
the field.
and
It's
it
like adding more
especially
cooling. It's just not that easy.
no, and it gets worse when we have to start changing motor sizes and we bump
Yeah.
from 40 to 50 horsepower motors, and we have to start having to change the drives, and
VFDs
it
and yeah.
it gets
Yeah.
ugly. So um, I like to avoid that at all costs because it's just not fun.
Yeah, me
Okay,
too.
so if we understand, one of the basic component parts of a pump curve is understanding the different numbers that are on the curve. So if I look at the left hand side of the curve over here, that is my head losses. Okay, that's my system head. And across the bottom is flow rate. Now, this particular one, it's in gallons per minute. This may say down here times 100 times 1,000 times 10,000. So we keep the numbers small, and you just have to figure out whether you're in the tens, hundreds, thousands, whatever. Okay.
Mm-hmm.
Then we have, our system curve, which is that line, that parabolic line right there. Okay.
Mm-hmm.
And so that's what we're doing. And we derive a system curve. A system curve is derived, it's a mathematical calculation, because we know that as our flow goes up or down, the system head loss moves up and down from zero flow, where we have zero head, all the way up to maximum flow, where we achieve maximum head. And head moves up and down by either the square or square root, depending on whether we're going up or down. Okay. And this is all related to the affinity laws. So if I look at pump curves, and I look at pump curves in their individual component parts that we see when we're looking at a pump curve in anybody's, hit the button there, curve data. Okay.
Mm-hmm.
So the first curve that we have here, okay, what we have here is that is just a standard pump curve. Okay. So we go from over here, and this is known as shutoff head on this side, and this is known as run out. Okay. Once you get out in this last 10, 15% of the pump curve, you really don't want to run there. Okay. You start to get into the unstable region of the curve, and yes, we show it out that far, but you
Mm-hmm.
really don't want to be running out
It's
in
just
that
because the
range.
pump's just spinning so fast because of lack of pressure.
The pump is trying to move a whole bunch of water, and the velocities are real high,
Mm-hmm.
and it's no different than a fan curve. When you get to the end of the curve, strange things start to happen.
Right. Right.
And so
Gotcha.
keep in mind, fan curves and pump curves, we're moving a fluid. Okay. It's
Mm-hmm.
just with pump curves, if the fluid gets out of the pipe, you get wet. In a fan system, if the fluid gets out of the ductwork, you just get blown on.
Right. Right.
Okay. So the next curve we look at is our system curve. Okay. So that is just a mathematical calculation from zero flow, zero head. Okay. And normally it starts down here at the bottom, but zero flow, zero head, all the way out to the end. Okay. It's just a mathematical calculation. Every one of us that builds pumps, we will plot the system curve for you, because you tell us what your design flow and design head is, and we can do the
Right.
math from there.
And
Okay.
those are determined by the test stand setup you went over earlier. So many
Well,
pipe diameters,
the
set
design
in
flow,
under ideal conditions.
right. The design flow and design head comes from the design engineer, and then all the curve data comes from us putting a
Right.
pump on a test stand and knowing what that blue pump curve is actually going to look like. So when you see a pump curve, when it comes out to you as an engineer, what you're getting is the intersection of the two, where the system curve and the pump curve intersect. That is your operating point. That's the duty point that you've selected, or you've said, hey, Mr. Armstrong, I want a pump that'll do 5,000 GPM at 100 feet ahead. And that's where that dot's going to be. Okay. So that's what
Gotcha.
that is. So next thing we got to look at, and this is where pump curves start to get a lot more complex. Okay. Because we put a whole lot more lines on the pump curve.
Yeah.
Okay. The first thing that we're going to look at is we may have multiple impeller sizes shown on a curve, because we build pumps with a lot of different impeller sizes. It may be the exact same pump, same casing, same motor speed, I should say, because the horsepower is going to change a little bit as we move up and down on impeller size and flow and head. So we may show, this is what's called a family curve. Okay.
Mm-hmm.
And in a family curve, what it means is we're going to show all the available impeller trims that we build for that particular casing size. Okay. So that's why it's a family curve. But nothing's changed any. There's total head. Okay. We have it in both feet and meters, because we got to serve both markets. Okay. So there's our headline. There's our impeller diameters. We have another line on here called NPSHR, which is net positive suction head required. And sometimes NPSHR numbers show up here at the top. Sometimes they're down here at the bottom. Most of our curves, they're down here at the bottom, and there's a chart that'll tell you what that scaling is. Then the next thing you see is these isobaric lines on the curve, those are the efficiency lines. Okay. So as you move back and forth across the curve with different impeller sizes, you notice your efficiency is moving around. Okay. And that's how efficient we're using the motor power and how much of that we're using effectively and efficiently. Okay. And then this last line here, this green line, that is our motor horsepower line. So you see we start down here at 200 horsepower is the smallest one way down here. And it goes up 250, 300, 350 on up to a 500 horsepower pump. Now, some things to pay attention to. Okay. Everything we show is done based on a specific gravity of 1.
So if you got glycol in there, it's a whole different
Right.
ballgame.
When you
Gotcha.
actually do your pump selections, okay, family curves are always based on water because that's what we have to do. We have to establish a benchmark, and it's 65 degrees and plain water. When we move into an actual selection and you tell us in the selection what fluid type you're running, whether it's ethylene glycol, propylene glycol, calcium chloride, some other form of brine, you have to tell us all that. You also have to tell us the operating temperature. If you don't tell us the operating temperature, we're going to assume 65 degrees. Well, as we all know, if I have ethylene glycol or propylene glycol in the system, as I start to drop the temperature, my specific gravity and my density change, okay, which will affect horsepower. So understand normal chilled water system, if I'm operating at 45 degrees or 42 degrees, ethylene glycol or propylene glycol, temperature really doesn't bother the horsepower significantly, not enough that you're ever going to notice the difference. However, been working on a job with a large customer. They are running 15 to 20 degree propylene glycol in the system. That makes a
Gotcha.
huge difference on specific gravity and density. So it changed what we had to do from a pumping standpoint. It bumped our horsepowers up a little bit. We also have the same issue. One of the things we're seeing in the data center world is starting to see more and more single phase and two phase immersion cooling systems. Okay, where the servers are actually sitting in a tank of liquid. That liquid is a dielectric heat transfer fluid. Yes, we can pump it. It's not a big deal. We may do some different things depending on the fluid. We have to change pump seals or something like that, but we can pump it. Understand that stuff is basically an oil. Okay, it's kind of a mineral oil based kind of product. So as we do those, specific gravity and density plays into that as well. So if you get one of those applications, reach out to the guys at Insight Partners and they'll work with you. They'll work with us and we'll get the right pump selection for you. Sometimes we have to bump horsepowers to make it
Right.
work. Okay.
Hey,
So
Tony, I got a question here if you want to
sure, go for it.
take a quick question. And for those watching, please ask questions. Gives Tony a chance to get a glass of water and rest a little bit. So we always appreciate that. Paul Holloway asks, those efficiency curves are only mechanical efficiency, correct? Question mark. As opposed to water to wire efficiency.
This is a combination of mechanical and hydraulic efficiency, which is what we're required to publish based on HI. So we take
as opposed to what is meant by water to wire? Is that actual job site?
No, wire to water efficiency is what we're looking at, which is all about motor horsepower and how efficiently we're using the motor horsepower. Okay. So, we have a certain, if you look at a pump curve or a fan curve, we may require a 450 horsepower motor, but the absorbed power may only be 400 horsepower. Okay. Or
Gotcha.
the brake horsepower. So what we show is that combination of the two for hydraulic efficiency and absorbed power efficiency. Because that's how we have to rate pumps based on HI and DOE and everybody else.
Gotcha. I've not heard that term before. And
You're
thank
kidding.
you, Paul Holloway. Maybe I've heard it, but I haven't heard it in a while. I'm not sure. Interesting.
You've spent too much time on the air side, young man.
Yeah, pumps are new to me as far as a rep as in the last couple of years. So yeah.
Okay. So if we
Nice. Well,
look
thank you,
at a
Tony.
pump
Thank you,
curve,
Paul.
if
Yep.
you look at a typical pump curve, one of the things that we see today is variable speed pump curves. Okay. Now you notice it kind of looks like a regular pump curve. Okay. We got flow, we got head, we got a system curve here. So that's the system curve I was telling you about that we plot for you. Okay. And that's your design point. There's your motor horsepower line. So I've stripped a whole bunch of stuff out of this. In this particular application, this is a variable speed curve. Okay. So these are not impeller sizes, because in a variable speed application, I can't change the impeller out. Well, I can, but every time you wanted to change the flow in the system, you don't want to change the impeller out. So we put variable speed drives on to be able to move the pump back and forth and change the flow rates. So what's going to happen is these are our speeds. So this is 100% speed, uh, 80, 60, 50, 40, on down to minimum speed. Now you notice there's another line on here called the average load, or the QPC curve. That's that orange line. That's known as the quadratic pump curve. What that actually is, if we look at a system and we know what the system curve is, we know what the design point is. And when engineers, as you design systems, you say, you'll tell the building automation guy he's going to put a differential pressure transmitter out in the system and control to a set point.
Right.
Well, we know that if we look at it at the pump, the calculated value of what that should be is about 40% of the design head. So that's what we start down here. That's 40% of what the design head of the system is. And we start there and we move upward, and that's what we call the control curve. And if you use an Armstrong pump with sensorless control, where we don't need a sensor out in the building automation system, we use the Affinity laws and speed, power, and flow to determine where that pump is running at any point in its curve. We base it on a 40% minimum. Okay. And we calculate out that quadratic pump curve, and that's how we control. And that's what's going to control the speed of the pump, based on system differential parameters, as valves open and close and change the head losses in the system. Okay.
Gotcha.
So the next thing we have to look at is what's known as the best efficiency point of a pump. Now, if I look at the requirements of ASHRAE, and ASHRAE says that I really want to operate my pump between 85 and 125% of the best efficiency point. And I'll show you a slide in a minute as to what that number really means. So if I look at my pump curves, okay, here's my pump curve, there's my operating point, there's my efficiency curve, okay, and I'm running at 85% of best efficiency. That's an ideal spot to be, okay? And understanding that you're going to maximize the life expectancy of the pump and minimize pumping system problems as long as you're in that 85 to 125% of best efficiency range. Okay, so if I look at this curve, and this is really what we're putting out there, every pump has an allowable operating range. Okay, and that is the range at which that pump can operate over its operating curve. But understand that there's also the preferred operating range. And as long as I operate within that preferred operating range, I'm going to avoid all the bad things that can happen to pumps, like cavitation damage. I avoid suction and discharge recirculation, because there's no physical seal on the impeller inside that casing. So the discharge water can actually move through the casing and go back in onto the suction side. And I get I get discharge recirculation. If I have excess wear at the impeller eye, I can get suction recirculation there. All those things can happen if I'm operating further and further away from best efficiency point. We also start to change thrust loads. We start to affect bearing and seal life, and we get higher temperature rises across the components in the pump. So we got to pay attention to all these things. And this is why we all are really, really concerned with best efficiency point, and why pump selection is so critical. What typically happens, is pumps are designed, engineers specify a pump and they go, well, I want the best efficiency at the design point. Well, you really don't want the best efficiency at the design point, because we know that that design point is done at the ASHRAE 1% condition. If it's done at the ASHRAE 1% condition, what's that mean? Means that you're spending 1% of the time at that point. That means that 99% of the time you are at something other than maximum capacity and maximum flow.
Right.
So why do I want to pick a pump that has its best efficiency at the design point when I really should be picking a pump that has its best efficiency at somewhere between 50 and 75% of that design point?
Right.
Because
Makes
now,
sense.
because that's where it's going to spend most of its life. It's a variable speed pump, so it's going to slow down. It's going to spend 90% of its life in that 50 to 75% capacity range.
So how
Why
many
not?
pumps are selected like that in that range?
The vast majority of pumps are selected for best efficiency point at design point, because that's what we did for years and years and years and years and years, because that's the way we design constant speed systems or constant flow systems.
So what do you
And
suggest for a designer right today? Like if he needs a pump curve, what do you suggest he asks for?
we want best efficiency to the left of the design point, so
Gotcha.
that pumps are selected for best efficiency to the left side of the curve, where that pump's going to spend most of its life. And it's looking at the pump selection and understanding that variable speed range and where that pump's really going to operate, and understand that the design point is there because we have to meet that. Because the last thing as engineers we want is we never want a phone call from a customer said, "Hey, my building's too hot, I don't have enough cooling."
Right,
Okay.
right. So you want to make sure it doesn't take away any safety factor.
Right, right.
Right.
But we need to understand that and understand how to maximize our life expectancy, how to maximize um, our energy efficiency, and get the best bang for the buck over the life cycle
Right,
of that
right.
pump.
Stacy Henson says, "Yep."
That's awesome. We got an engineer that gets it.
Thank you,
So,
Stacy.
yeah, no, that's great. I mean, I talk to so many engineers that don't understand that, and they look at me and go, "Nobody's ever explained that to me before."
Yeah.
And
Well, that's why you're
you
here.
explain it,
That's why we
well,
have you.
and this is the cool part. Once you explain it, they go, "Duh."
Right, right.
um, so understand what happens when we run off BEP. Okay, so we get excess vibration as we decrease flow. We start to increase the vibration in the pump. Okay, because we're decreasing flow and increasing the head on the pump, so we're putting more load both radially and axially on that pump shaft. We start to get suction recirculation, and we run the discharge pressure up. Okay, so we're wasting energy when we're doing that. Okay. The other problem is when we have high run, when we get towards the end of the pump curve, we get far right on the pump curve. Now we start to increase vibration. We get really, really ugly radial loads, and I do mean ugly. We get, as you move further right on the curve, the NPSHR curve goes up exponentially, and the further right you go, it actually we've got some pumps that it almost becomes a vertical line. It's so steep. Um, and the other thing is we drastically affect the component life. Okay, so we're reducing the seal life, we're reducing bearing life. Whether you're affecting motor bearings or pump bearings, you're going to have an impact on the bearings. The other problem is as you get further and further right on the curve, what actually happens is you increase the potential for damage to the impeller caused by cavitation. And cavitation is basically the pressure you see in the pipe is not what the pressure is at the eye of the impeller. What's in the eye of the impeller is significantly lower than what's in the pipe. Keep that in mind. Okay. Because that net positive suction head is what's actually pushing water into the eye of the impeller. Okay. So this is what we're talking about here. Okay. Net positive suction head required, that's the little R, is the amount of force necessary in order to push liquid into the impeller of a centrifugal pump in order to mitigate cavitation. to meet our stated performance. Net positive suction head available, that's the little A, is the amount of force at our disposal from the environment to push a liquid into the impeller of a centrifugal pump. Now, we've all used NPSHR and NPSHA for years and years and years. Okay. Understand that we want the available to be about 30% higher than what the required is. The reason for that is there's things we can't control as engineers. Okay. I can't control system cleanliness. Okay. As good as all of you may be as an engineer, there's no way you can control how clean that system's going to stay.
Mm-hmm.
You can't tell me and guarantee that that owner's always going to go clean those pump strainers on the suction side of that pump every week like they're supposed to on a tower system. Okay. I've been out on jobs way too many times. The customer calls, oh my God, my pump's cavitating. It's falling apart. Somebody's running gravel through it. And you get out there. And by the way, if you didn't know, that's what cavitation sounds like. Somebody threw a handful of gravel into the pump. And that's because the little water bubbles or little micro bubbles in there are exploding. We're basically trying to make steam. We're boiling the water inside the pump, even though it's 85 degrees. Just remember that little chart, if everybody's looked at a steam chart, that, I can make water boil at 85 degrees by just reducing the pressure low enough. But there's a new number called NPSH3 that has been bantered around by ANSI and HI. And what this is net positive suction head 3%. That net positive suction head required in feet that will cause the total head of the pump to be reduced by 3%. Okay, that's what it really comes down to. And they're trying to come up with a better way of defining NPSHR, because NPSHA and NPSHR has been so confusing for people. And the other thing is that the NPSH3 value, we know if we get close to that, we're going to decrease the performance of the pump. We're not going to get the flow out of that pump that we're supposed to. So this is the reason HI is talking about adding this to the HI standards. And so now you guys got a first look at what's coming.
There you go. Breaking news.
Yes. So when we look at net positive suction head or NPSH, remember, keep this in the back, keep this in mind. NPSH charts are always written in absolute pressure. They are not written in gauge pressure. Okay. So we got to look at, so this is the formula for calculating NPSHA. So that's your atmospheric pressure head, your total suction head, minus the liquid vapor pressure at pumping temperature. So you got to take into consideration, and I've had way too many guys not look at the vapor pressure of water at, if you're designing a condenser water system, is not taken into consideration that water is 85 degrees. It'll come back and bite you. And then you and I have to have the ugly discussion of how we're going to fix the pumps and put different pumps in or change impellers. And we never like having those discussions because they're not fun. And I'd much rather, if you're not sure of how to do it, or you're not sure about your calculations, call me when you're in design. I'm more than happy to sit down with you and go over all your numbers. That's what I get paid to do, is keep problems from happening before they happen. So when I look at, what's going on in a pump, this is a really cool little animation that kind of shows you this is what's going to happen in cavitation and what's going on in the pump. Okay. So if we look at this, we test the NPSHA at the inlet, which results in a 3% head drop at constant flow. This is the NPSH3 or the NPSHR number. Then when we look at it, when the inlet pressure is not sufficient, the additional pressure drop in the impeller eye results in that pressure below the vapor pressure, and it causes bubbles. That's really what's happening inside the eye of the impeller when we're cavitating. Okay. And then as those bubbles collapse and the pressure rises through the impeller, the bubbles cause erosion damage inside the casing. Okay. And they will erode things. I'm going to show you a picture here in a minute of what happens. You'll be amazed. If real quick question for everybody. How many of you ever seen a pump taken apart that's been cavitating?
I have not.
Okay. Anybody in the audience taken a pump apart and seen what it looks like when it's been cavitating? I'll take the silence as a no.
I'm having a little so if you're logged into the chat, thank you. I understand from a text the chat is full, so I'm trying to add more capacity to the chat. So I apologize. First time we've streamed live on our website. So we'll get some answers for you here in just a minute, Tony.
Okay. So if you remember what I said about 30% margin, if I go back and read the HI standards, and by the way, if any of you guys really want some really good sleeping material to read, go buy the HI standards and read them. It's a real headbanger. There's a lot of great information in there, but if you really want to understand pumps and fluids, go read the HI standards, and you'll learn way more about pumps and fluids than you ever possibly could have wanted to know. But if you read 961, that talks about the HI standards for guideline for NPSH margin, and it is 30%. There's a couple manufacturers out there that will tell you, oh no, you only need 25%. I'm telling you right now, if you design with a 30% margin, you and I are going to become best friends, and you're not going to have problems with pumps. We'll just solve it at
That's
that.
good. Yeah, we did get
So,
some chats. Nick Maffeo, I hope I'm saying that right, says he has not seen that. Jay Brown, we took one apart yesterday, so he's recently seen that. Jay Brown said, yep, thank you, Jay. And Kimberly Stroud says that she's seen it. And I believe I repaired the chat, so now we can have more people in the chat. So if you haven't logged in yet and can give it a try, I think Chris Hudson was having trouble. Just let me know via text, Chris, if that doesn't work. Sorry,
cool.
Tony.
So
go for it. I'll keep updating you on the chat.
The pretty picture right here, that's what an impeller looks like that's been cavitating.
Oh
Now,
my gosh.
that is horribly severe cavitation.
Now, how long would that take to happen? And Chris says the chat's available to accept more users. So thank you, Chris. Go ahead, Tony.
So that damage, that was about 9 months worth of damage. I've seen other pumps run in worst cases of cavitation. I did a job several years ago at a municipal water distribution facility, and they were pulling water out of a tank, and whoever did the original design assumed that the water level in the tank would always stay at the top all the time. Well, the building operator or the plant operators decided that they didn't like using flow meters to determine turns, because in a municipal water system, you have to have so many turns on your storage tank in 24 hours. Well, the only way these guys knew how to calculate turns is they'd let the water level drop all the way to the bottom and then refill the tank, and then let it drop and refill the tank. And this, mind you, this was a 100 and some odd thousand gallon tank, so it was not a little tank. But because the engineer designed it to maintain the level all the time at the top, as they dropped the level in the tank, the NPSHA constantly moved up and down. They took less than 3 months to do damage that looked like that to the impellers, and they did it on 2 pumps that were, I want to say, 100 horsepower apiece. And all they did was they just kept buying new impellers. They didn't understand what they were doing.
Well, it's good if you're in the impeller replacement business, I guess.
Yes.
A couple things here. Welcome, Hakeem. Eduardo says he's seen it a lot. Wendell, glad you're in the chat now. Thank you. Sorry for the issues. PFox at Newcomb and Boyd, what is the recommended location to read suction pressure on a pump with a diffuser? Good question.
So, to answer that question, I like to read my suction pressure about 2 pipe diameters before the diffuser, and then immediately downstream of the suction diffuser. Now, the downside to doing it through the suction diffuser is, depending on the size of the suction diffuser compared to the size of the inlet flange on the pump, because a lot of times we'll have an 8-inch pipe suction connection with a 6-inch flange connection going into the pump. Understand that when I read that at the suction of the pump, or near the suction of the pump at the outlet of the suction guide, I may have to take into account velocity pressure or the velocity head that's being imparted to the water at that point. And if I look at it and I understand that, I can take that into consideration when I'm calculating the capacity of the across the pump and where that pump is actually running on its curve. And so just so everybody understands, when I look at a pump curve, okay, so here's my pump curve. This is showing the NPSHR curve. Okay. And you notice how my flow is moving upward. So I'm moving further right on the curve. Notice the NPSHR is going up. This one's actually a pretty curve. It's not real radical out here at the far end. But you notice, we're going from about, probably about 20 feet ahead, and we max out at about 45 feet ahead, maybe 50 out here at the end. Okay. So if I'm out on the job site and I want to read what's going on, if I read the differential pressure across the pump, so I take a suction pressure reading and a discharge pressure reading, and I subtract the suction reading from the discharge reading, and it tells me that I've got 100 feet ahead, I can run that out on the 100 feet ahead line, and where I hit my pump curve, that's how much flow. Now I come straight down, bingo, I'm moving 1,250 gallons a minute at 100 feet ahead with this particular pump. Understand, when you take pressure readings across your pump, use one gauge. Don't use two different gauges. Because if the gauge is wrong, if the gauge reads 10 pounds high, it's going to read 10 pounds high when I read it on both sides of the pump.
Right.
But if I got one gauge reading 10 pounds high and one gauge reading 10 pounds low, I just added a whole bunch of error to my reading. If I use the same gauge for both readings, even if the gauge is wrong, my differential is still correct. The difference between the two readings is still the difference. Okay. Mathematically, it's still the same number. So the other thing to consider, and test and balance guys typically will use a differential pressure meter. There's a whole bunch of them out there on the market. TSI makes one, Air Data makes one, Alner makes one. There's a bunch of different ones out there. Hydrobalance makes one. And it has two hoses on it. You put a hose on each side of the pump for high and low, and it'll read the actual differential across the pump. If your design firm doesn't have one, I really suggest you get one. They are invaluable in going out and troubleshooting what your pumping system is doing and how it's behaving and how it's operating.
Gotcha. Thank you, Tony.
So let's talk a little bit about the pump affinity laws, okay? And understand, this is what they look like mathematically, and understand speed and flow are directly proportional, okay? So at a fixed diameter, if I decrease the speed by 50%, I just decrease the flow by 50%. It's really simple, okay? Head moves as the square or the square root, depending on whether I'm going up or down in flow, okay? And brake horsepower, and this is why drives are so great, brake horsepower moves at the cube root, up or down. Okay, so if we design our pump for maximum speed, maximum flow, full power, as we drop the speed, power goes down by the cube root. So we get much, much lower input horsepower. Okay.
Gotcha.
So the real simple summary of the affinity laws, okay, flow rate varies directly with pump speed. That's the easy one. Okay. Head varies as the square of the speed. That one's a simple one. Power absorbed varies as the cube of the speed. So a 10% reduction in speed results in 0.9 times 0.9 times 0.9, okay, 90% of the speed, equals a 27% reduction in absorbed power. That's significant. Okay. Little bitty change in speed, big change in power.
Right.
Okay. So start thinking about that. And that's why that's why the energy code says, hey, we want VFDs on pumps. We want variable speed pumping because it makes a huge difference. Okay. So what you want to always do is take advantage of the affinity rules and understand, by the way, that the affinity laws are the same whether we're dealing with pumps or we're dealing with fans. Okay. Doesn't change any. Okay. So understand this is what's happening. Okay. So the strain is my um, flow and speed. Okay. The middle curve line is my head. So at 80% speed, the head is 64%. Um, at 80% speed, we're at 80% flow, and at 80% speed, power is reduced to 51%. So understand that's where all this is going, and that's what's happening with this. Okay. So when we look at this, we understand that our pump curve can be adjusted for different speeds. Okay.
Hmm.
So you look at our efficiency curves, you look at our system curve. Okay. And we start looking at what's going on as we start to slow that pump down. Now we're starting to move back and we're getting into different energy ranges and different efficiencies, and understand that under with certain pumps we're going to lose efficiency as we move back left on the curve. And this is why it's really critical to pay attention to impeller sizes and efficiencies and where we're selecting that pump. Okay. Now the other thing everybody has to pay attention to is minimum speed on a pump, and every pump's a little bit different where its minimum speed has to be.
Hmm.
So I, as a general rule, somewhere between 20 and 30% is the minimum speed. Some pumps it's a little bit more, some pumps it's a little bit less, but kind of keep that in the back of your head that that's not a hard and fast, got to be this. It can change a little bit depending on the pump. Okay.
Gotcha.
So understand, if we understand what's going on with our pump and we understand how the impeller size can affect the pump curve, because the pump curve is based on the impeller size, right?
Hmm.
So when I look at that, understand that I as a manufacturer get to adjust the impeller size when we select the pump to maximize efficiency, use of horsepower, and velocity flows within the pump casing. So ideally, as we start to change the impeller size, so if I look at this, this is the maximum impeller size. This is a 90% curve. Okay. So I'm getting a better match. And what we really want to do is really minimize how much we change that impeller size. We want to do everything we can to not put full size impellers in and then go, okay, we'll trim them down after it's in the field. You really don't want to do that. Let us figure out where it really needs to be based on your system design parameters, and don't go, oh, I got to have a full size impeller, because that's not necessarily going to get you the best mix of horsepower and efficiency.
Right.
Okay. So when we look at all this, we understand that, you know, there's our design point. Okay. So if we need to, if the resistance is higher than design, okay, what are we going to do? Well, we can increase speed, okay, to handle, higher heads, or we can decrease speed, you know, depending on what we're trying to do. Okay. And we're trying to stay, here's the original curve right there in the middle, and we're moving the system curve around based on what's actually going on in the system. Because we know, as an engineer, we don't have any control over how the mechanical contractor actually pipes the system. We do, because we lay out a drawing and say this is where we want the piping to go, but he may add or subtract fittings to the system that you didn't account for. One of my
Hmm.
best examples, when I was working as a consulting engineer, they started the system up, and the contractor and the tab contractor called me up and say, man, we got a huge problem. The system head loss is just, it's like 2.5, 3 times higher than what you showed on the drawings. And of course, we're not getting the right flow because we moved way back left on the curve. And, we got big problems. The water source heat pumps aren't working right, and all that. And so I go out to the job site and I'm looking at the pump and I'm going, something's not right. I mean, I went back and back checked all the design work, and I wasn't the designer. I was head of forensics at that time. And I'm out looking at the job, and I'm talking with the design team, and I'm going, guys, something's not right here. So I started going out of the mechanical room and poking my head above the ceiling. And I noticed something kind of weird. At every point that a pipeline got to a piece of ductwork, there were 490s at every piece of ductwork. So the mechanical contractor let the sheet metal contractor do the coordination drawings, and the sheet metal contractor went, well, the piping can't run through the ductwork, so I'll just put 490s to go down, over, and back up around every piece of ductwork. That added a whole bunch of uncalculated and unplanned for head loss in the system. Rather than change the elevation of the pipe or change the elevation of the ductduct so they didn't run into each other, the sheet metal contractor just thought, okay, well, I'll just add 90s. Talk about just thoroughly destroying a job.
Yeah, that'll get you there.
Yes. So understand that, when you go out and look at a job and you take your readings across your pump and you're trying to figure out what is going on in your system, and you're seeing weirdness, you're seeing head losses that are higher than what you designed it for, and you're pretty confident in your design, get out of the mechanical room, stick your head above the ceiling, and look. You would be surprised at what you will find looking at the system. I've had jobs where I've found valves 25% open, and everybody's running around like chickens with their head cut off going, oh my God, you didn't design the system correctly. Mr. Engineer, you're an ignorant fool. You don't know how to design. And it's going to cost us thousands and thousands and thousands of dollars to fix this design error. And you got an owner that's screaming at you going, how could you do this? And when you get into those situations, take a giant step back and go, this is really kind of simple, guys. We're just moving water around the building. I'm not building the space shuttle. I'm not sending men to the moon. I'm not sending rockets to Mars. And remember, men built the building. Nothing against, I'm not saying anything against men or women. It's just human beings built the building.
Right.
And pipe fitters, I love pipe fitters. They're a great group of guys. But sometimes they do things because they don't understand. And so they do things because it makes their job easier.
Right. They're trying to get the job done just like everybody else.
Exactly. And they don't understand the implications. Right. So anyway, if we look at a closed system and an open system and what happens to the pump curves, we move back and forth on the system curve as the system resistance changes. So understand that what you design for head may not be where it's really going to operate. And most time it's going to lower. It's going to go down. So this is where having a variable speed drive comes in handy, that if we say that, hey, look, the maximum speed run of this pump at design was supposed to be 55 hertz. You may want to slow it down to get it to come back on the curve where it's supposed to be at that new lower resistance. And one of the advantages of Armstrong's integrated drives is we have the ability to recalculate what the system operating head is and recalculate that control curve internally without anybody having to do any math. It's all built into it. It's called auto flow balancing. And at some point, if anybody wants to have another discussion about that offline, we can be more than happy to do that.
Yeah, and if anybody wants a copy of these slides, I don't know if that's okay, Tony. We can.
Yeah, it's not. We can.
So as we wrap it up here, a little bit, well, pretty much on time. Any questions? Let us know in the chat. We'll give Tony a little bit of a break here. So a few things. Keep your browser open. We'll be here all day. Our next class is at 11, and that's going to be with cooling tower selection and design with Mark Pfeiffer with Marley. So he's going to be coming out of Kansas City, Missouri at 11 o'clock. So just leave your browser open. So yeah, we will. So thank you, Emmett, I believe. I'm sorry if I'm not pronouncing that right. We will have this on our YouTube channel. That leads me into the next part of this discussion. So our YouTube channel is accessible down. If you look below this video, you're going to see the schedule for today. You can also go right now and download the PDH certificate for this class. So it should be the first button there on pump curves and problem analysis, Armstrong. You can go ahead and download that. If you're having any issues with that, or if you want a copy of the slides, go ahead and email me. And my email address is on this webpage that we're streaming to here on our website, right below the chat box. So if you look below the chat box, you should see my email address, tmormino@insightUSA.com. Go ahead and email me there. Again, down below, you'll find the PDH certificate. You will also find links to two things that we work hard on. One is, thank you, Leonard Lowell. It says great, informative presentation. I got several of those, Tony, by the way.
Cool.
You'll get a PDH link. And again, please stick around. We'll be here all day. We got 3 more amazing speakers coming on. You'll also see links to HVAC TV where you can subscribe. That's our YouTube channel, where we probably get about 3 subscribers a day and about 20 hours of views a day on there. So you can go check that out. We have a podcast as well. It's called the Engineers HVAC Podcast. That question might come up later, the Engineers HVAC Podcast. And you can check that out below too. The links below. You'll hear me and Tony. Actually, Tony's been on there a couple times. He's been on our YouTube channel a couple times. You can go subscribe to that. If you click on those links, it should open a separate window. So you should be able to view it that way. So what we're going to do now is we're going to try to do a trivia question, and we're going to give away one of these amazing Insight Partners OtterBox mugs. And these are really cool. I guess I call it a tumbler. We're going to ask a trivia question. First person to answer that in the chat is the winner. Insight Partners, please do not answer the questions. We'll keep this open for our customers. And the rule is it has to be domestic shipping only. So if you're in the domestic US, please participate. We did get a question come in here. We'll do the trivia question here in just a moment. Gavin Button, great presentation. What would be the test and balance method for establishing the zero flow head point for a sensorless pump installation?
Okay, so you put the pump in hand. You look at the pump curve, figure out what the pump design maximum speed is, because a lot of our design envelope pumps are not 60 hertz. They could be 50 hertz, could be 55, could be 58. It's all about maximizing efficiency and impeller trim. You run the pump up to that speed. You close the discharge valve on the pump very slowly. Don't slam it closed. And read the differential pressure and the suction pressure. And the difference between the two is the shutoff head pressure. It's that simple.
It's just that simple.
Yep.
I'm just typing a quick chat.
Right. The key to it is do it at the design maximum speed. Don't automatically, because one of the things that the job I was telling everybody about was out in California, and the test and balance contractor did his testing at 60 hertz because that's what he's always done. And the pumps were designed to operate at 52 hertz. Well, if the pump is running at a higher speed than what is design max is, guess what? The pump moves up, and it makes you think that there's a bigger impeller in that pump than what is actually in there, because the shutoff head's going to move up.
Gotcha. Thank you, Tony.